Hello, welcome to the video for 9.4, Introduction to Functions. By this point in the year, we're not actually being introduced to function. We're actually going back and reviewing a lot of the concepts we have seen this year already. So we're going to go pretty fast here. But starting fresh, starting over, what is a relation? A relation is a set of ordered pairs. That's really all it is. At the end of the day, any set of ordered pairs, x and y, is considered a relation. The x's of those ordered pairs is called the domain. The range is the y's. So most of the time we call the x's the input or the domain, and that we call the independent variable. Those are the ones we plug in. They are independent of what's happening in the relation. The range is the output of those variables, what you get out of that relation, and therefore they're dependent. They're dependent upon x. Now, a relation is a function if it fits a couple of criteria, okay? So a function has to be what we call 1 to 1. We're going to go ahead and write that one down. 1 to 1. Okay, not 1, the number 2, but 1 to 1. Basically what it means is for every input you have only one output. Okay, now they can have the same output. That's okay, but you can't have one input, one independent variable, one x, going to two different dependent variables, two different ranges, two different outputs, okay? So let's look at these. Example 2 here. I'm sorry, the first one up here, example 1, is this set of ordered pairs a relation? The answer, of course, is always yes. So, yes. Second, example 2 here, are the following relations? Absolutely. Every single one of these is a relation. So we can start with yes, yes, and yes, because they are ordered pairs. Even these second two here, they're evens and odds, that's still a relation. They're relating each other. They're relating independent variables x's to dependent variables y's. Are they also functions? That gets a little more restrictive. So in this first one here, we see that the domain, maybe let's start with that question. What is the domain here? We're going to write this in function notation. D. So a little curly bracket. The domain is going to be all these input values, all of these independent variables, 1, 2, 3, 4, 5. Now, if we look at those domain values, do we ever see one value going to two different or going to the same output value? Sorry. If we see 1 going to 2, but we also see 1 going to 5, that's not a function. So let's check out these ranges as well. We've got 1 going to 2, sorry. 2 going to 4, 3 going to 6, 4 going to 8, 5 going to 10. For every domain value, we have a unique output. There is a single output. So yes, this is a function. Fabulous. Now you may even see a pattern here. You can do more things, but we're going to pause right there on that one. So the second one is also a relation. What's the domain here? The domain looks to be about the same. So again, curly bracket, we look at all those input values. 1, 2, 3, 4, 5 seem to be the things that are in. Notice I'm not writing like 1 to 5 because that's not true. A 2.5 is not in that domain. So I have to be very specific. 1, 2, 3, 4, 5. That's it. All right, what happens? 1 goes to odd, 2 goes to even, 3 goes to odd, 4 goes to even, and 5 goes to odd. So is this a function? You may hesitate to say yes because we see a bunch going to the same place. 1 goes to odd, but 3 also goes to odd. 5 also goes to odd. So you'd think, no, this can't be a function. They're all going to the same place. But for every domain, there's a unique output. We don't see 1 going to two different ideas. 1 is not both odd and even, right? 1 is odd. That's it. At the end of the day, that is the output. There is a unique output for 1. So this is a function. You don't see any of these numbers taking on both odd and even. That's not possible. All right, but if we were to reverse that, we get this relationship in number 3. We have the domain has changed now. The things we are inputting, the independent variables, are odd and even. And there's only 2 options here. I see odd, even, odd. Right there. We don't need to list all 5 of them just because they're used 5. These are the 2 things that are in this domain, odd and even. Now here we have a problem because if I say what dependent variable goes with odd, you have options for correct answers here, and that's a problem. We have 1, 3, and 5 both all coming out of the input of odd. So if I say, oh, plug in odd, you have no idea what the answer is. It could be 1, 3, or 5, and so this is not a function. If you have multiple destinations, multiple outputs, multiple dependent variables for your answer, then it is not a function. All right, example 3, determine if the relations separated by this or represented by the sets of ordered pairs are functions. What is the domain of each? Very similar. So this is now a hardcore relation. Let's do this a little faster. The domain, easy peasy. -2, 1, and 3. Okay. Domain in the second relation, -2, 1, 2, and 3. Oh, that's a horrible 3. Let's write that again. 3. All right, domain's super easy. Just had to grab all those independent variables. If I happen to see one listed twice, I don't write it twice, okay? And that's actually going to help me draw something here. So which one of these is a function? One of them is and one of them is not. Notice how in the second one, we have really the only difference is this point right here. The second one, that is a unique 2 goes to 3. 1 goes to 3. Now they are going to the same place in this second function, right? 1 goes to 3, 2 goes to 3, but that place is unique to both of them. There is one singleton answer. So this is the function. Whereas in the first one, if I say, where does 1 go? You don't have an answer to that. You can't say it goes to 3, it goes to 4, and have someone be wrong, right? You have 2 possible correct answers. And so this is not a function. Now, the second one, later this chapter, we'll talk about what it also is not. It is something we call not onto, meaning it doesn't have a unique destination, no unique dependent variable. But that's not necessarily a requirement for a function itself. It's just kind of a more specific function. All right, let's do it again, but this time we're going to use an equation itself to determine if these relations are functions. So relations can also be equations. You can write any equation you want, but does that make it a function? No, not necessarily. Just because there is an y equals on the page does not mean it is a function. So example 4 here, y equals 5x minus 2. What we want to look for is there something that we can plug in for x, our domain, x is domain. Is there something we can plug in for x that will spit out 2 different numbers? Well, what happens with multiplication? Does multiplication ever spit out 2 separate numbers? No. 5 times 1 is 5. 5 times 2 is 10. 5 times 3 is 15. And you could keep going, right? But even with the decimals, even with the fractions, even with 0, even with negatives, all multiplication is what we call closed, meaning it does not spit out multiple answers. Does minusing 2 ever do that? Nope, minus is also the same thing. Subtraction is what we call closed, is not going to affect. So we can plug in anything we want. The domain here is negative infinity to positive infinity. Fraction 0, it's all included. And so yes, this is a function. Let's look at the second one here. Not a format we're kind of used to. It may be a little hard to tell at this point if it is a function or not. Let's rearrange this real quickly so that it says y equals. Not an absolutely necessary step, but sometimes a little easier, okay? So we're gonna go ahead and subtract 1 to the other side, y squared, square root it, we get that y is equal to the square root of x minus 1. And this just kind of rearranges it so we can look at our independent variables a little faster, rather than being so dependent on our dependent variable. So if we're looking at our independent variable here, is there anything we could plug that in and get 2 different answers? Actually, yes, we could. If you remember, there's a unique aspect to a square root. There's a lot of numbers that do not exist, right? There's a lot of numbers that don't exist. And so if we plug in a -1 here, or even a 0. If we plug in x equals 0, then we're going to have a -1 under the square root, and that does not exist. Now, in our original format, -1 was fine. If you plugged in -1 for the dependent variable, you just get 2 answers. And so this is not a function. All right, this last one, let's look at this. Let's do the same thing. We've got y cubed is equal to 1 minus x squared, and then the cubed root of that. And again, this is not the way you have to do this. If you want to look both at the independent and dependent at the same time, you could leave it in the original format. But for me, I think it's easier to separate my y out so that I can look at what I'm plugging in and how it's going to affect coming out. Now, a cubed root is not actually a problem. A cubed root's okay. But if I plug in -1 to this function, that thing's going to square. I'm going to get 1 minus 1, and cubed root of 1 is 1, so I'm good. I'm going to get the same thing if I plug in 1. But is that a problem? Is plugging in 1 and -1 an issue? No, remember, you can have two different x's going to the same y. That's fine. But there's no way out of this one that I'm going to get two of the same y coming, or no, I'm sorry, two different x's, one x giving me two different y's. So I'm not going to get one x suddenly producing two different things. And so this is a function. Now, in case you didn't draw any conclusions on that, notice notice the cube here, the degree 1 over here. Odd degrees are great. When you have squareds, 4th powers, 6th powers, that's where you start running into a lot of issues with functions, okay? Looking at your dependent variable there. All right, the next way you can determine if something is a function, and the last thing for this video, is by looking at a graph itself. Not the most convenient option is to look at the graph, but you know what? Sometimes we are given graph information, and that's all we have. So let's take a look at these three graphs here. We can do something called the vertical line test. Remember, the vertical line test is banking off the fact that it needs to be a function. If you have a function, that means that for one x, you only go to one y. Again, that can be the same y, that's fine, but it cannot be one x going to two different places. So let's look at this first guy here. When we draw a line down this function, a vertical line, we see that this one place, x equals 2, has 2 points, 2, 1, and 2, -1, and therefore this is not a function. That's what we call failing the vertical line test. Okay, a vertical line will instantly show you if you have one x value going to two different y locations. Okay, let's do it again on this circle over here. If I could draw many vertical lines, it would fail at many, many points. Now, not every vertical line has to be failed or passed. It's one single vertical line and you're out of the game. And I found one there. So this is not a function. Very pretty circle, but not a function. Has an equation, but not a function. This last one we have to be really careful about. If I draw a perfectly straight line, I'm going to try and draw a perfectly straight line here. Actually, you know what? I drew a perfectly straight line over here, so I'm going to copy that, and I'm going to borrow it. If I draw this perfectly straight line and I move it all the way across the function, I don't know anything else beyond this. I don't know if it curves back again and does something weird, but if I move this along all the function, notice that line never touches it twice. And so this is definitely a function. It passes the vertical line test. So yes. All right, that's it for the introduction to functions. We'll next talk about domain and range and work with some function notation in the next video.